This video is on Unit 1, and it is just kind of going to hit the key points for this unit. So the first thing that we talked about was just the different states of matter. The main thing to know this is just to be able to recognize the different particle diagrams. So we know that a solid has a regular arrangement. We can see that they're all nicely lined up in columns or rows. They're kind of touching each other. We do know that solids do vibrate in place, so they're not totally still because they do still have some kinetic energy, just a very low amount of energy. They also have strong forces. That's what keeps them attracted to each other. Those forces between the particles, that's what keeps them held tightly together. Liquid, we can see there's a little bit more energy. There's a little bit more space in between the particles. They're starting to move around more. And then our gases, they have the most kinetic energy and essentially no attractive forces. Those particles are free to expand and take the shape of the entire container. For physical and chemical properties, just being able to recognize the difference. So physical properties is usually something we use to describe. So something like the size or the color or the length, the mass, something like a measurement that you can take about something. Chemical properties is something that actually changes the substance. So that could be something like burning. That could be actually reacting, like reactivity, reacting it with a different element. Trying to think of some other chemical properties. There's not really very many. I was thinking physical properties. Some other ones are boil, melt. Something where you might be changing the physical state, but you're not actually changing the substance that you have. Like if I boil water, I still have water. It just went from liquid to gas. Intensive and extensive is very important. So intensive, you can think about it like internal. So it does not depend on how much matter it has. It's not going to change that property. If I have a little bit or a lot of it, it's an internal property, an intensive property that isn't going to change. So it could be something like color. Like you have a white piece of paper. If you cut it in half, you've changed how much you have, but it's still white. The way something tastes, one apple tastes the same as 10 apples. Melting point, boiling point, it doesn't matter how much water, it's still always going to boil at 100 degrees Celsius. It might take longer to get there, but the temperature remains the same. Extensive properties is something that does depend on how much you have. So you can think about it like an external measurement or something. So mass, right? Like one piece of paper is going to weigh differently than 500 pieces of paper. Volume, length, shape, all of those are things that can change if you have more or less of something. When we're talking about the gas laws, we have all these different laws. You do need to know kind of the general relationship between these variables. So pressure and volume we know are always opposite, or something that we call indirect or inverse. It just means that if pressure goes up, the volume's going to go down. And then temperature and volume are direct, meaning they move the same, and then temperature and pressure are also the same. So you can think of those kind of like, a spray can, like a can of spray paint. If you throw that in a fire, right, it's going to speed up the movement of those gas particles. Increasing the temperature causes an increase in volume and an increase in pressure. So those kind of are always going to move the same together. The key thing here is that we can actually use these equations to do some calculations. So the easiest thing to do, and this is the formula that is on your reference sheet, the purple sheet in class, is to use what we call the combined gas law formula. So like if I look at number 1, it says a sample of nitrogen occupies a volume of 250 milliliters at 25 degrees Celsius. What is the volume at 95 degrees Celsius? So in this case, this does not say anything about pressure, so I can actually, well, I didn't mean to take all of it out. I can actually take out the pressure of my formula. And I can just ignore it. So I have volume and temperature. So now I can plug in my values. So I'm looking at, it's starting off with this information, right? So that's my ones. So I have 250 milliliters. And then remember, anytime we talk about gas, right, my temp has to be in Kelvin. So I'm going to take 273, and add it to the 25 to get 298. Okay, now I can look at my second V2. So I'm looking for V2, and then the temperature is 95 degrees. So I'm just going to use my calculator, take 95 plus 273, and that's 368. So in order to solve for volume, I can just cross multiply. So we end up with V2 times 298, and that's going to equal these two multiplied together, 250. I'm going to run out of space, 368. Okay, so then I have V2 times 298, and that equals 92,000. So then I can divide by 298. So my final volume is 309. I'll round. Okay, so we can just plug in. So if I look at question number 2, it says a sample of carbon dioxide occupies a volume of 350 liters at 125 kPa. And then it asks what pressure if the volume is 2. So in this case, we do have pressure, but there is no temperature in my problem. So I can just ignore the temperature in the formula. So now I can just plug in my P1 and V1. So that's this first thing that's given to me. So 125 times 3.5, and that's going to equal, it's asking for pressure, and then the volume is just 2. So we're just plugging it in. Then I can divide by 2 on both sides so that I can cancel that out. And then my final answer is 218.8. You could round to 219 if you wanted to. So that would be our answer. So technically with sig figs, it would be 219. For number 3, it's talking about a helium balloon. We have a volume and a temperature and a pressure, and then we have some other information. So in this case, we're going to use all of our variables. So let me change my color. So pressure, right? The first information is always our ones. So we're given 820. So I'm just plugging that in. My volume is 50. Now this is 25 Celsius, so I do have to add 273. So I get 298. Right? That's the same as right here. Now I can look at the other side. It's asking me for volume, so that's going to be my unknown, but it does tell me my pressure is 650, and then my temperature is 10 C, so I do have to add that to 273, so we get 283. So we can cross multiply. Okay, so we end up with, here I'll do one side at a time, so 298 times 650 times the volume, and that's equal to 283 times 820 times 50. So when you type in your calculator, right, we are going to eventually divide by these so that they cancel, but if I do that to one side, I have to do that to the other. So I'm going to multiply everything on top. And that is 820 times 50. And then I'm going to divide by everything on the bottom. And make sure you actually hit the divide button. Like I typed in, 283 times 820 times 50 divided by 298 divided by 650. So make sure you divide by both of those. And so your final volume comes out to be, we'll just round to 60. And this is liters. Liters because it's liters here. So 60 liters. So remember, we're always just going to use this formula and just plug in our information. The next topic is heat and temperature. The main thing to know here are just these two definite definitions. Heat is the actual energy and temperature is just a measure of the energy. And then we always know that heat is transferred from hot to cold. That's why, if you go outside, open the door to your warm house to the cold outside, you're letting the hot air out. Okay, so, and this is just a picture showing the same thing. So all the energy here is going to move over to the low energy side. Let me add one more thing here. This formula is the one we use when we talk about heat transfer. So Q is the energy, M is the mass, C is the specific heat. That's something that will always be given to you usually. Sometimes you'll have to calculate it, but if you can just remember C, specific. And then the temperature, this is always your final minus the initial. So it's okay for this to be in degrees Celsius because we're not talking about a gas here. We're usually talking about water or some other kind of metal that's getting hotter, because you're putting it next to something that's hot. So we can actually measure how much energy is absorbed by looking at how much the temperature changes. For phase changes, this is just kind of knowing the general steps and where to label. So we'll only really look at water for the most part, but we know as we add heat, we're going to change our state over time. The main thing is, here at this point, the temperature is increasing because the particles are moving faster. Remember, temperature just means energy. So if we're getting higher temp, that means higher energy. So those particles are moving faster. Once we get to this point, we can see that those particles are starting to separate. So they're moving so fast now that they're actually breaking apart from one another. So we're breaking those IMFs, those intermolecular forces, attractive forces that are holding them together in that solid state. Now we have a liquid, we're just increasing our heat, adding heat, increasing our energy. And then again, we get to a certain point where now we're going to start breaking away from each other and forming a gas. So we're breaking our IMFs here and here on those flat lines. For the phase diagram, we can answer a couple of these questions. You're just going to be reading a graph. So what state of matter is present at minus 80 degrees and 6 ATM? So we just kind of look, my graph here, I know I can see that I'm moving downwards. Like here's minus 56, minus 78. So minus 80 is probably like right past that. And then a 6 ATM. So if this is 1, 5, 6 is probably just maybe kind of right above it. So I'm just going to look and see where do those two points kind of intersect if we go up and down. And that's right there. So I can see I'm firmly in the solid area. Okay. For number 2, it's asking about a phase change. And it says, here, I'll change my color. It says What phase change occurs if the temperature changes from minus 75 to 5 and a constant pressure of 2? So let's say our pressure is right here at 2. Okay, so I'm saying if I'm at minus 75, so minus 75 is, a little bit less than 78. So let's say this is where my points intersect there, right? And then it says I'm changing my temperature. I'm going towards 5 degrees. So I'm going this way, right? It's getting warmer over to the 5 degrees, which it doesn't really matter where it is, probably somewhere in here. But I can see that I'm going from a solid over to a gas. So when we go from a solid to a gas, that's called sublimation. That's like our dry ice, how it goes from a solid to a gas. So it may be helpful. This is kind of the extra phase change that you need to know. So obviously melting and freezing, and then vaporization is from liquid to a gas, and then sublimation is from solid to a gas. So you do need to know that. All right, scientific notation. Your calculator can do this somewhat for you. The main thing you're doing is just moving the decimal. So if we look at this first box here, right now my decimal is right here. And when we do scientific notation, we always want the decimal after the first number. So that means I want to move it to right here. So I'm going to count how many times I move it. 1, 2, 3, 4, 5. So now this number becomes 3.34 times 10. And I know it's going to be a 5. And because this is a big number, my exponent is going to be positive. So I'm going to leave it like a 5. Okay, for number 2, I want my decimal after the 5. I move it 3 spaces. So my number is times 3. But because this is a little number, like less than 0, it's going to be a negative 3. Okay. Here, I want my decimal after the number. 1, 2, 3, 4, 5, 6, 7, 8. And because it's a little number, less than 0, it's going to get a minus 8. Okay, for these, I'm going to move my decimal this many places, and I know that because it's a negative 3, I want to move my decimal to the left because I want to make a little number less than 0. So 1, 2, 3, and then I can just fill in my decimal, my zeros. Again, this is a little number, a negative 4, so I want to make a little number. So I'm going to move it 4 places. 1, 2, 3, 4. And then now I have a positive exponent, so I want to make a big number. So I'm going to move it 5 places. 1, 2, 3, 4, 5. And then just fill in my baskets with zeros. For accuracy and precision, just know the main definitions and be able to kind of and look at some data. Accurate, you're always just looking to see if it matches the actual answer, right? The known value. Precision is just how close you are to each other. So if I make 5 measurements and they're all really similar, I'm pretty precise. Okay, so here's an example of that. I won't go through all of them, but we know water boils at 100 degrees. And so this group got right at 100. So this would be the most accurate. Okay, number 2. Excuse me, I had to sneeze. Most precise is which group's answers are all really close to each other. So if I look, this one's going all the way from 100 to 102, so that's pretty far away. This one's even further, 90 to 95. That's a huge range. This one, though, is pretty close. They're all within 1, 99 to 100. So the most precise would be 3. Significant figures, it's just based on precision. Remember, you're just counting the real numbers. If there's a number with a, I think I have some practice here in a minute. We'll look at those. Yeah, I do. Okay. So let's start with just reading measurements. So remember, the last digit should always be a guess. So here, I know that it's at least 21, so I'll just guess maybe 0.7 for the graduated cylinder. Each of these little lines is going to be 0.1, right? Because this is 4 to 5. So I know these big lines are the ones. So this is like 0.1, 0.2, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. So if I was to read this, I would say 4.9 for sure. And then my guess is going to be a 0. If you said 4.89, that's fine. The main thing is just to make sure that you have that guess at the last digit. If we compare these two rulers, the bottom one, I'm only certain that it's at least 2. So my guess is going to be maybe something like 0.8 or 0.9. Then if I look at this ruler, and I kind of have to zoom in so I can count, but let's say 1, 2, 3, 4, 5, 6, 7. I think it's maybe closer to like 2.75. Okay, so again, this is my guess because I can see that it's at least 7. It may not be all the way to the 8, but it's at least to the 0.7. When we do significant figures, any number 1 through 9 is significant, and if I have zeros stuck in the middle, then I count them. So here, I just count 1, 2, 3, 4. 4 significant figures. Here, 1, 2. 2 significant figures. When I start getting into the numbers with zeros, I have to remember my Pacific and Atlantic. So if the decimal is present, I'm going to start from the Pacific. So I'll put a little P and a P there, okay, because those are my 2 Pacifics. So I'm going to start going this way. I can't start counting until I get to a number. So this has 3, okay, Pacific, skip over that. Now I can start counting at the 8, so that has 4. For my ones that have an absent, I'm going to start from the other way, the Atlantic. And again, I can't start counting until I reach a number. So I'm going to skip the zeros. Now I can count. So there's 4. Here, skip the 0. There's just 2. For multiplication and division, your answer is always in the least. So, for example, this has 2 significant figures. This has 4, so my answer would need to be in 2. This has 4. This is present, so I'm going to start counting as soon as I get to the 4. So that has 3, so my answer would be in 3. For scientific notation, we're just looking at the first part. We don't really care about the exponent, so that has 2. This has 3, so my answer would be in 2. And then you could say times 10 to the whatever if you needed to. Okay, same thing here. This is just 2. This is 2, so your answer would be in 2, and then times 10 to the whatever. Last thing is density, just being able to use plug in values into the formula. So this formula is on your reference sheet, on your purple sheet when you need to use it. So we're just going to plug it in. So this is talking about a cube. So remember, a cube is a 3D shape. And it says the sides are all 3. So that's 3, and then that's 3 also. Remember, when we find the volume of a cube, it's always length times width times height. So in this case, it's just 3 times 3 times 3. So your volume is equal to 27 centimeters cubed, I think. 9 times 3, yeah. So now I can just plug it into my formula. My mass is 2.1 divided by 27, and you would get 0.078 or so, and that's just grams per centimeters cubed. Okay. For number 2, we have a liquid. So we measure volume in milliliters. So here's my sugar volume. In this case, it gives me the density, 0.843, and it gives me the mass, but it doesn't give me the volume. So I like to use the triangle when I'm doing any of these calculations. So you just plug it in. You can see exactly the way that it looks. It goes into the triangle. So density on the side, M and V on top of each other. So if I wanted to plug, if I'm looking for volume, then my formula is going to be, I'll write it up here, M over density equals volume. So when I plug that in my question, the mass was 75.2, the density is 0.843, and that's going to equal my volume. So in my calculator, I type that in and I end up with 89. Whoopsie. 89. And this is volume, so it's going to be milliliters. So that's it for Unit 1. Let me know if you have